June 22nd. The grind continues. Another day, another dollop of misery on this website. The hyperbolic, there's a new Discord now. It's called the Hyperbolic Coding Chamber. So this Discord is absolutely jumping right now. So you might want to get in soon before the slots fill up. But just throwing that out there. So back again, another day. Kind of want to move a bit faster, but I gotta start going slower, I think. Don't want to go too fast because the whole point is to like teach it to myself basically, and by talking about it and figuring it out or explaining it to someone else, then it helps me understand it more. But I should probably go a little slower. But also, I kind of want to get to harder problems, but can't rush the process. Right now, I think 20 to 40 minutes a day is like the max that I have in my guts to give to this godforsaken website. But yeah, so that's a lot of time. It's actually not that much, but it's what I can consistently commit. So right now it's looking like a minimum of 20 at a maximum of an hour. But I always set the bar really low because it's really easy to meet. And the Atomic Habits book mentioned stuff like this. So just trying to keep it easy to continue. And I feel like 20 minutes, I think the added benefit of doing it every day is that I kind of have to come into contact with exactly why I can't do it every day. So for example, I was running into an issue where if the later and later it got into the day and I hadn't done it, the more and more I would dread it. But I only realized that having to go through it every day. So it kind of let me basically speed run figuring out the best way to make sure I can do it more frequently. And so one of those things is keeping the time limit really short and doing it as early as possible. But even then there's a little bit more nonsense to it because I really got to strike when the magic strikes my bones, then I really got to just do it. So enough rambling. It's 20 minutes. I have one to do today called read end characters given read 4, and I feel like I can already visualize the solution. But I'm going to try and do some random ones, and if you run out of random ones, then we'll do a new one. But yeah, I really just want to get to harder problems, but you can't rush the process. So it is what it is. I'll try and go slower, but we shall see. So I'm just going to jump into it. Whew. Okay. So read end characters given read 4. So, and the goal is going to be linear time complexity with constant space complexity. I think it's been a little while since I did this one, but we have a definition for read 4. Read 4 is a function which takes an array of strings as input and returns a number. I think read 4 and read 4 match up here. It looks like we have a function expression being saved into the variable solution, so I'm guessing they're going to call solution. But we're returning a function, or it's basically going to end up as a closure, basically. And we're closing over the identifier for the function read 4. And I guess the code that we're supposed to write is going to go inside this function. But if there's any extra state we wanted, we could probably keep it up here, but unnecessary for this problem, I think. I'm just going to write the goal so I don't forget it. It was linear time with constant space complexity. So, given a file, let me check if I'm recording. We're good. Given a file, let me start my timer. Got it. That's what I mean. Let me slow down. Given a file and assume that you can only read the file using a given method, read 4. This must be this method here. Implement a method to read end characters. So it looks like we have the definition of the method read 4. API read 4 reads 4 consecutive characters from file, then writes those characters into the buffer array buff4. So this must be the input array they mentioned up here. The return value is the number of actual characters read, which matches to the output parameter there. Note that read4 has its own file pointer, much like file*pnc, definition of read4. So you have car array buff4. So it takes a parameter, which is buff4, which is an array of strings or an array of characters. In other languages, but in JavaScript, it's just going to be an array of strings. Buff4 is destination, not a source. The results from read4 will be copied into buff4. Okay, so we read 4 characters from the internal file pointer, copy them into buff4, and we return the number. Below is a high-level example of how read4 works. The first call of read4 is A, B, C, D. We read 4 characters from the file while passing in buff4, and buff4 will get the value A, B, C, D, and we return 4. The second call of read4 A, B, C, D, we read 1 character from the file, hence read4 returns 1. Read4 returns 1, right? And we can see that buff4 gets overwritten with A, B, C, D gets overwritten with buff4 equals E. We return 1 character. We read one more time, it reads an empty character into buff4, and we return 0. So that's how read4 works. We need to use read4, implement the method read, which must be the function that the solution is actually going to have, that reads n characters from file and store it in the buffer array buff. Consider that you cannot manipulate file directly. So buff is a destination, not a source. You need to write the results to buff. Consider that you cannot manipulate the file directly. The file is only accessible for read4, but not for read. Our function will only be called once, so it has to be able to do it in one go. You may assume the destination buffer array buff is guaranteed to have enough space for storing n characters. So this can dynamically enlarge in JavaScript, but I guess for other languages, we can assume it always has enough space. So basically the question is, using a function that can only read 4 characters, read an arbitrary number of characters. So you could do this with linear time and linear space by literally reading the entire file. So read the entire file to memory and then read an arbitrary number of characters file to memory. You can read the entire thing into memory and then just read the arbitrary number of characters they want us to read. Right, but that would be linear time with linear space, and we can do a little bit better. So we can do linear time with constant space if we, instead of reading the entire file into memory, we'll keep a local buffer of 4 characters and copy those 4 characters into buff before we read another 4 characters up until we read n arbitrary characters. So what does that look like? What that's going to look like is 2 for loops, and well, one is going to be an inner for loop, the other one's going to be an outer for loop, right, until we read the number of characters we need or the file ends, right? So it's easier to use until the file ends. So we'll say while cars read equals 4. This is just going to allow us to simplify how we iterate the first iteration of this problem. So say while cars read equals 4, right? Cars read equals 4, it means like, hey, we read 4 characters from the file, right? We can continue reading. Let's operate on those characters that we read from the file. Well, what we said we would do was go to an internal buffer and then internal buffer to buff, right? So to create that internal buffer, we'll create temp, which equals an array. And then we're just going to call read4 with temp, right? And we know from the original problem description that it's going to set temp equal to whatever it can read from the file, but it's also going to return a number, which is defined up there. So this is probably sort of small. Right? So if it's going to return a number, then we want to know the actual number of characters read, right? And so that's when we actually are going to set this to cars read. So this is how we actually continue with the iteration after the initial iteration, right? So now we have four characters or 0 characters read into temp, right? And what do we say we would do with that? We'd say we'd copy that from the internal buffer to buff, right? So we're going to have let I equals 0, and we're going to go to the number of characters read, right? I plus plus. The reason we can set it for cars read equal to 4 in the beginning is because look at this. If we set it equal to 4, right, we'll get into this while loop and we'll try to read 4 characters from the file. If the file is empty, cars read actually gets set to 0. And if cars read is 0, then this for loop isn't going to run. We'll exit out of here and cars read will be equal to 0. And in that case, we can just return cars read, right? But we're not going to do that just yet. Here we're going to copy from the internal buffer to buff, right? So the internal buffer is temp, right? So we want to copy, right, from temp to buff. Well, how do we know what indice to copy and buff? It means we're going to need one more variable, which is going to serve as sort of a pointer. And it's going to serve as the last index we copied into buff, or the next available slot in buff. It's going to start at 0, right? So buff sub copied is going to get the value of temp sub I. And we're going to increment copied, right? But as we're copying these, the function as it is now is going to copy the 4 characters into buff, right, on each iteration, going almost endlessly, right? The goal of this function originally was to read n arbitrary characters, and so we have to abide by that. So if copied equals n, right, then we're just going to return copied. And what this allows us to do is that once we copy, let's just say 3 characters into buff and n equals 3, well then we're done, right? All we ever wanted to do was read n characters by using a function that can only allow us to read 4 characters, right? And it might look a little strange to have it before, right? We do our copying, but it's important, right? If we put it outside here, right? If we were to call this function and say, let's copy our file equals ABCDE, like here, and we want it to read 0 characters. Well, our function, if we put it here, actually can't copy 0 characters. Because as soon as you get into this array, you copy at least 1 character, which means the minimum number you can copy is 1 character. So we want to put it up here, which means the minimum number you can copy is 0 characters. It sounds a little strange to be like, hey, why can you copy 0 characters? But it's just safe to write code that way. And so we'll return copied. And then if we make it out here, we can return copied characters as well, which will be the number of characters we copied into buff4. So you have to return copied. Additionally, this also covers an additional case in the sense that if we copy ABCDE, let's just say our file has ABC in it, and they want us to copy 2 characters only, or actually want us to copy 4 characters, but there's only 3 characters in the file, cars read is going to get the value of 3, right? And then we're going to copy 3 characters in the buff, right? But copied will never equal n because there's only 3 characters in the array and they want us to copy 4 characters, right? And so what happens there? Well, this loop would end because on the next iteration, cars read would read character from the file and it would actually return 0. This would not equal 4, so we'd pop out. We want to return copied, which would be 3. We only got to copy 3 characters to the file. So let cars read go copied, const temp. Cars read equals 4. Then we're good. And then if we have temporary buffer, cars read equals read 4, so temp. Read 4 passing in the temporary buffer. Bar equals 0, I less than cars read. Internal buff to buff. 0, we're copying this for loop's going up to cars red. And we're copying on each iteration, copy equals n, then return copy, buff sub copy. Right, so we're going to copy all the values from temp going up to cars red into buff plus 1. So I think this should be good. Took a long time. So this should work with linear time and constant space. The reason it's constant space is because at max in memory, if we subtract the memory needed to store this into buff, because we're assuming that's part of the output. If we subtract that, then all the memory we're actually ever keeping, aside from that output, is this temporary buffer, which at max can hold 4 characters. So we only ever hold about 4 characters in memory, and that's why it's constant space. Binary search tree. So we have sorted array to BST, we have nums, number, we have an array of numbers that we want to convert to a binary search tree, right? And so given an integer array nums, where the elements are sorted in ascending order, so our input to the function is going to be an array of numbers sorted in ascending order, converted to a height balanced binary tree. Height balanced part just means that we're going to have to select the center as a pivot on each iteration, on each recursive call, which the depth of the 2 subtrees of every node never differs by more than 1. So to do that, we can create a function, right? To do that, we're going to need a function called helper. This function is going to take 2 parameters. Left, which is going to be a number, and right also be a number, and we're going to pass in the numbers array. It's going to return a tree node or null. Right, when we start, we want to pass in our left range because we're just going to be implementing a binary search over this array, and then well, it's going to look like that, and then we're going to recursively, we're going to do an in order traversal. Wait, I think I'm getting confused. In order traversal. And our left side of the range would be nums at length -1, passing nums. And if left is less than equal to right, which means our range is valid. If our range is valid, then we want to actually, continue to create the nodes. Otherwise, we want to return null if our range is invalid. Our binary search tree is going to look I know the code to write. However, I want to make sure that I understand it. I think I'm confusing this problem with another problem which is similar, and I think that other problem is, in that problem we're creating a array. We're creating an array in ascending order from a binary search tree. From a binary search tree. From a binary search tree. At the same time, in-order traversal of a binary search tree produces an array in ascending order. Yeah, I'm confusing this with another problem. And it's not that I don't know the code to write, but I'm trying to sort it out in my head. I think sorting out those two different problems in my head is going to help. But the original problem is another problem where you're given a binary tree and you have to produce an array. And I think in that one you do an in-order traversal by passing in the array and pushing elements onto the array using basically in-order traversal. So in the other problem, we're converting an array, we're converting a binary search tree to an array, sorted array, and in this problem, we're having an array we're converting to a binary search tree. It's interesting that it's basically the same, except a few lines are swapped, I think. That being said, we'd have to create a node, right? Before we create the node, we actually want to calculate our pivot, which is always going to be left plus the math.floor, just because this is JavaScript of right minus left. So we do right minus left, and then we do over 2 semicolon, and then we have our minimum, which is our left. Push it over a bit. Once we calculate our pivot, and we're going to have a left-leaning binary search tree because we're flooring it, which means that in the case where we have to choose between two nodes of our pivot, we're going to choose the node on the left. From here, we can create a new tree node, and from the constructor above, we can pass in nums subpivot, and then node.left is just going to, we're just going to call helper, going from the range of left to pivot -1. Since we just created a node for the pivot, we're going to pass in nums, duplicate the line, same for right, except we're going to go from pivot +1 going to right, and then we're going to return the node. So what this looks like is pretty much stack based because it's how recursion works. We call this with the range 0 to 2 if we use a small array of just 0, -3, 0, and 9. And then we create the node at 0, go left, right, go left again until we can't, and then go back to here, go right, pop that off the stack, go right. But it looks, I think the other thing, it also looks like, I think it also ends up looking like pre-order because, you know, we're doing NLR and it's technically supposed to be in order, but I think the difference here is that it's just simpler since we're not actually calling any code for the main node, right? We're just setting a value. But I think this is technically the same answer. If you do pre-order, you would just do const value like this, and it doesn't really change much, but you end up needing the node. Right, that's the problem. You end up needing the node to be created. But I guess one way you could do it is just say const lval equals helper, and then you do const node equals new tree node, Yeah, I guess, okay. Yeah, this wouldn't work either. The problem is literally just that you do it like this, and you could still do NLR. Val, it would just be nums sub pivot. But I think it ends up reading like it's pre-order just because of how you have to arrange these operations. But it's technically in order. So this would be linear time, I think, because our operations are going to be linked to the number of elements in this number of in the array. But at the same time, number of space we'll take by using recursion is going to be it's going to be bounded by the height of the tree. That's actually wrong. Recursion type requires O log of n space because the tree is height balanced. Because the tree is height balanced. Because the tree is height balanced. Interesting. Yeah, I think we just need more recursion problems to get a hang of why, when things are log of n, when things are bounded by the height of the tree. But that's an interesting difference that I have noted in my head. Now try to keep cognizant of in the future. I'll do one more for moves. Actually, I'll do two more, but move zeros isn't too bad. So function move zeros, we have nums, which is an array of numbers. Given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Note that you must do this in place without making a copy of the array. So it's not even going to be constant time. The space should be O of 0 because we're not supposed to use any space. So input 0, 1, 0, 3, 12, and they want us to move all the zeros to the end. So I think you can do this with the sliding window pattern. What exactly the window is keeping track of is the sliding window pattern the window is keeping track of is the group of zeros that we are constantly shuffling towards the end. So the way we could go about handling this is you could have the way the sliding window pattern typically works is you have some variable which represents the left half of the window. For this one, we'll call this last 0 idx. We'll set it equal to 0 to start, and we're going to iterate over all the arrays, all the numbers in the array exclusive of the end. And then on each iteration, if the current number, which is going to be the right, our I variable is going to be the right side of the window. if I equals 0, we want to keep going actually. If I doesn't equal 0, num sub I doesn't equal 0, then we want to swap it with our last 0 index and increment our last 0 index. So if num sub I equals num sub I does not equal 0, then we want to swap them. I think I remember this now. I ended up making a mistake here last time where I just set it equal to 0, but you still have to swap the number itself and not use 0. So the number that we want to swap first is actually going to be nums sub I, and then we're going to save the value of num sub I because we're going to replace it with num sub last 0 idx, and then nums sub last 0 idx is going to get the value of 10, and then we're going to increment last 0 idx. And I think this should be what we're going for, but we can run it in our heads really quick for nums. So last 0 idx equals index 0, I equals 0, num going to nums.length, incrementing by 1. So does num sub I, which is 0, not equal 0? Well, it does equal 0, so we're going to keep going. Then we're going to be at index 1, but it's really index 2. We're going to be at the second element in the array. Does num sub I not equal 0? Well, it doesn't equal 0 because it equals 1. So const temp equals num sub I, and then num sub I gets the value of num sub last 0 idx, which is still 0, which means 1 gets the value of 0. And then num sub last 0 idx, which is 0, gets the value of temp, which is 1. And then we increment last 0 idx to be index 1. So now we have 1. After one iteration, we have going from 0, 1, 3, 12 to 1, 0, 3, 12. Okay, and so we're going to continue. We're going to go to index I equals 2. Well, does num sub I, when I equals 2, equals 0? I mean, not equal 0? Well, it does equal 0, so we keep going. Does num sub, so I equals 3 now, does the number at the element of index 3, 0, 1, 2, 3, not equal 0? Well, 3 doesn't equal 0, so const temp equals nums sub I. We're going to save this value. Nums I is going to get the value of last 0 idx, which is index 1. So we're going to put a 0 here. And then num sub last 0 idx gets the value of temp, which is 3. And last 0 idx gets 1 pushed forward, which is going to be the 0 here. Okay. From there, we're going to keep going. We're going to get to our final element, which is 12. And for 12, we're going to say, does 12 not equal 0? Well, it doesn't equal 0. Temp gets the value of num sub I. Num sub I gets the value of last 0 idx, which is 0. Num sub last 0 idx equals temp, which is 12. Last 0 idx plus equal 1 goes to here. So this should be linear time with in place space. And I think there was one thing I noticed with the time space, with the sliding window pattern. The right side of the window it always excludes the next element until the next iteration. So if we imagine this is a sliding window between like iteration 0 and 3, our window only really ever has the current element of last 0 IDX going up to the I minus 1. So that's probably something important to note. Now keep in mind for future sliding window pattern problems. Binary tree in-order traversal. Was this the problem I was talking about? This was the other one that was messing up my head. So we have function in-order traversal, root, we have a tree node, or the root node in this binary tree, and we have to produce an array. Given the root of a binary tree, return the in-order traversal of its nodes values. This is just a binary tree, it's not a binary search tree. But the in-order traversal, because this isn't a binary search tree, it's not going to be in ascending order, but we can do an in-order traversal, and that's just going to be recursively with L and R, in order, so we'll return a function called helper, which is just going to take so what we're supposed to return, given the binary tree, is an array. So for the function, for the sake of the recursion function, we're going to pass in an array of numbers. We're going to pass that into the array. We're going to pass in the root as well. I said return helper. We're not going to return anything. We're just going to return nums. This helper is going to return void. And so we just have to return an in-order traversal. So what does that look like? We're going to say if root, right? Otherwise, we're going to return. Otherwise, we're not going to do anything. Keep forgetting. We're not going to do anything. We're just not going to add anything to nums. So the first thing we're going to do is L and R. So since that's the case, yeah, it's so interesting. Yeah, I'm getting some, I think they call it interference. The mental model in my head of this problem with the other problem is confusing me. But I think that's a good thing, because detangling it should help both problems make more sense. So however I've categorized them subconsciously in my head is making them more difficult to reason about in the same like time frame. That's good, because they're different problems for a reason. I know that the solution is NLR, but the way I did it in the other problem, I created the node first by calculating the pivot. There's no pivot because we're returning a binary search tree here. And I think that might be what I'm confused about. I'm doing this. You don't have to calculate the pivot because this is a binary search tree. There's no pivot to calculate. The pivot is already encoded in the if root. Then we want to set the nodes. We want to push something onto the array. Now it would be Yeah, I think I'm seeing my problem. Or maybe I'm not. I want to say node.left equals helper, but helper returns nothing. So I feel like helper has to return a number so I can push a number on it. That's the only way I see the whole recursive thing working. That one of nums.push. Interesting problems. Nums.push. Yeah, major interference. Nums.push. Yeah, helper can't return void. It has to return something. I think it just, in this case, it ends up returning nums.push. If I'm pushing something, I feel like I could just write code and clicking run code, but I don't want to do that. So I feel like I have to understand it instead of continuing to do that. For some reason I'm stuck. Helper has to return something. I think I just made a mistake here. Helper has to return something. It's the only way I see it working. You can do nums.push helper root.left, pass in nums, and you can do node.val. Oops. You can do, so yeah, you can tell the interference there because node was the name of the variable in the last problem. And then you would do but in the case where it doesn't return anything, they don't want us to return anything in the case of null. But this is what an Inorder traversal would look like. So if we do root.right, I think this works. Oh no, well, no, it doesn't work. So I'm not even returning a value from the function itself. Yeah, I'm all over the place. This is technically LNR, which is in order, but I'm not returning anything from helper. So what am I doing? If I return nums.push helper root.left nums. In order traversal. All right, I'm gonna add a struggle timer. If I can't figure this out in 3 minutes, I'm gonna look at the solution. The struggling is good though, because it means I'm gonna learn something once I see the answer or I figure it out. We don't need 3 nums.pushes, we only need 1 nums.push. Because on each iteration we'd be pushing 3 times, which doesn't make any sense. I think we only need 1, because once you get to n, that's when you actually process the data. Otherwise we would go left or right. So if we're going left, if the root exists, then we want to go left. Well, if we call helper subroot dot left, nums. I think I'm understanding why I'm confused. I passed in the nums as a parameter into the recursive function, but I'm so used to returning, building the like a sequence of sub-expressions by returning, or like having to return something to actually get the value you need. But since I already have access to it, you can always just do nums.push. I think that I figured it out. You just have to call helper and root.right. And I was getting confused because it wasn't returning anything, but I have access to it. So root.left, pass in nums, and if root is empty, then you'd go back and then you do nums.push root value, and then you do root.right. If root.right is empty, then we just go back, and so on and so forth. I think this is correct. Oh yeah, oops. And this would actually still be void. Yeah, that was very... That was interesting. That was interesting. Yeah, I definitely need more recursion problems. This was very interesting. I think when they say L and R, N is where you actually do the processing, I think, and L and R are just the next visiting. So maybe there's 2 states. There's visiting, or I guess the mental model I use, there's visiting and then there's processing. N in LNR, NLR, or RLN is just when you do the processing. So if I was yeah, doing this iteratively I think would really help me understand. Follow up. Recursive solution is trivial. Could you do it iteratively? I'm going to set a timer for this one. So, recursive solution is trivial. Could you do it iteratively? So we're going to have to remove this function. And we want to do this iteratively. We're going to have const nums equals an array. We want to return the, because we're doing an in-order traversal of the values of the tree to an array. I think we need a stack, which is going to be empty to start, and node, which is going to start at root, or cur, which is going to start at root. And while cur does not equal null, I think this is about as far as I got last time. While cur does not equal null, so our root node isn't null. We would like to go left first. We'd like to go left first until we can't go left. So we'll say, have another one. We want to go as far left as we can. While cur does not equal null again. Then we want to say cur equals cur dot maybe we want to push cur onto the stack so we can return to it. We'll say cur equals cur dot left. This will allow us to go as far left as we can, I think, just with this, and then we'll have a stack which we can pop off to visit the nodes we visited in that particular order. So if we imagine a tree like this, I'm just going to change it to be 1, 3, 2, like this, instead of the way they have it right now. Inorder traversal of this would be L and R. So we start at 1, then we go left. Can't go left again, so we print N. Can't go. Yes, we put N, then we go right. There's nothing at right, so we print null. Go back to N, 1, then we go right, so we get 3, 1, 2 for an in-order traversal of this. So let's run this for the current code. We have nums, which is an empty array, stack, which is empty, cur, which is root. So while cur does not equal null, 1 is not null. And while cur does not equal null again, well, 1 is still not null. Then we're going to push 1 onto the stack, and then we're going to go to the left. And then we're going to say, hey, we're going to go while 3 isn't null. Well, 3 isn't null, so we're going to go left again and push 3 onto the stack. Now we have 1, 3. And then we're going to go cur equals cur dot left. It's going to be null, so while cur does not equal null, well, cur is null, so we're going to pop out now. So this is actually going to be the L portion. This is going to be the N plus R portion. So if we're null now, so we're null right now, right? And 3 was our last none visited, we're null. So what we want to do, we want to say cur equals stack dot pop. So now we're going to be back at 3 again. Now we want to do N. Now that we're at N, this is our processing step. So maybe we want to do nums.push cur.val. I'm going to do cur.val. And then maybe we want to do cur equals cur dot right. This would be the N portion, and this would be the R portion. Cur equals cur dot right. And now since we're right again, right, if right equals null, we're going to go back to the top. Cur equals cur dot right. If cur dot right, I think you need an if statement for this, because if cur.right is null, when we go back to the top, then that's what we're going to do. Then we also want to say if cur does not equal null and the stack.length does not equal 0. So this saves us from having to do an if statement. And the stack isn't empty, so cur.right for 3 here, 3.right is going to be null. We go back to the top up here, well, cur is null because 3.right is null, but the stack isn't null. So we're going to do while cur does not equal null. Well, cur does equal null, so we're going to pop the next element off the stack, which is going to be 1, push 1, and then do cur equals right. Well, right 1.right is not null, so we're going to push 2 onto the stack, and then do cur.left. Right, cur.left is going to be null. It's going to be null. and then we're gonna pop 2 off the stack, push the value for 2, go right. Right is null. I think there's not supposed to be a particular way to end it though. Okay, we're at 2. Let's just say we're at the end part of 2. Stack.pop. Okay, now 2 cur equals 2 nums.push 2 onto the array. Then cur equals cur.write. Okay, now we're at 2.write. Well, 2.write is null and the stack is empty. I think we might have figured this out. Please, please, LeetCode gods, please. Oh man, our array is empty. Oh, I think the problem is it's either while cur, we want to stop if cur is empty and stack.length is empty. If we De Morgan's law that, it should be while cur does not equal null or stack. We want this to run while cur equals null or stack is not empty. Oh my god, please, LeetCode gods, please. Let's go. Oh my god. No! Okay. Okay. Oh man, I didn't think I was gonna get that one. That's a feel strong, man. Kinda lucky. So this is what it looks like iteratively. This would be L, N, R. L and R, so it's double while loop. We have an N portion and then an R portion to break it up. I think conceptually that helps a lot. Glad I was able to do the recursive solution. I think it's important. I think going forward, if a problem has a follow-up, we'll just do it as part of the follow-up. But that's a wrap on time, my dudes. Make sure to join the hyperbolic coding chamber. I mean, you really don't want to miss the updates and the parties in here. I mean, it's going crazy. Might not be enough spots left, but yeah, that was day 8 or day 9. So hopefully by day 100 will be a problem. Right now, we're not a problem. So I'll be back on tomorrow for the grind. Farewell.